Ladies and gentlemen, boys and girls, welcome back to another video. This is my mom here.
Hello, everybody.
All right, so I've got a bit. Oh no, my video. I think the audio. Does it still? Okay, it still works. Well, the screen is frozen. Huh. Okay, well I guess we'll take that off. But okay, so hopefully you guys can hear me. I got something I came up tomorrow morning, so I won't be able to do the normal class, but we can just go over the midterm here, make it happen, and then if you guys have any questions, feel free to email me, and we can have a like a Zoom call or something later on in the day if anybody still wants to talk. But so all we're gonna do is I'm gonna go over every problem from exam 3, and that should be fine. So first off, we have does this following sequence converge here? And what we were looking for is we see that it's a sequence, right? So we don't want to get confused. It's like, oh, 1 over root n doesn't converge. So it's a sum doesn't converge, right? But the sequence, for sure, 1 over root n, right? You got 1 over root 2, 1 over root 3, and then so on, you know. Eventually, you know, this root n is going to go to infinity, so you're going to have 1 over infinity, you know, going to 0, right? So what we have here is an is cosine n over root n. Well, we know that an... How is cosine bounded? We know that cosine is bounded from above by 1. So 1 over root n, and then bounded from below by negative 1. So we got negative 1 over root n. Right, take a limit through. And then we're going to have the limit of the left-hand side is 0, right? Limit of the right-hand, of the middle is still going to be limit of an, and then the limit of the right-hand side is also 0. And so then we just say by squeeze theorem, we're going to have that this limit has to be 0. So this one was kind of quicker. Yeah, okay, so let's go on to number 2. So what is number 2? Oh, oh, shoot. No, we're fine, actually. I don't think I showed anything. I have to watch that back. Okay. Well, shouldn't have done that. Okay. Does the following series converge? We've got justify your answer e to the negative n. So there are a lot of different ways to do this. We can actually do geometric series, so 1 over e to the n, right? This is going to be 1 over e to the n, which converges as 1 over e is less than 1 in absolute value. Now it's positive, so you don't have to use the absolute value. So we could say by geometric series. You could also do integral test, which is what I was looking for. So, or not what I was looking for, but this is how I envision the problem being, right? So I'd say that f of x, so this is like, A. B, we could do f of x equals e to the negative x. We notice that this agrees with our sequence on the natural numbers. And so then this guy here, if you're going to use integral test, if you use any test, you have to make sure that you use all of the hypotheses, right? So we'd have to say this is continuous decreasing and positive, right? And so then we say this means the integral of e to the negative x dx from 1 to infinity is going to be what? Well, we're going to take this antiderivative. We're going to say limit as t goes to 0, or t goes to infinity, sorry, of integral 1 to t, e to the negative x dx. You go ahead and say this is the limit. What is the antiderivative of this guy? Well, it's going to be negative e to the negative x. So we're going to have negative e to the negative x evaluated from 1 to t. And this is going to end up being e to the negative 1 minus, this is the limit, right? Minus e to the negative t. But you notice that e to the negative t, this guy is going to go to 0, right? Because we're going to have 1 over e. This guy here, the limit of e to the negative t, right? We're going to be going down to 0 here. So that's just, that's how I would do this. And then you say, okay, well, by integral test, you're going to have the convergence, this convergence, 1 to infinity e to the negative x dx, has the same convergence as the sum of e to the negative n from n greater than or equal to 1, right? And so by this, then you just say, okay, well, as the integral converges, then the sum also converges. If you had the integral diverging, you have the sum diverging, right? So you could do something like this for 1 over n or something like this. You integrate 1 over x, and then you'd notice that that is going to go to infinity. And so then you would have the sum diverging, right? Okay, you can also do ratio test, right? The hydrogen bomb versus coughing baby if you'd like. You don't have to. I saw somebody do that. They're like, oh man, can I just, use the same test for everything? I was like, you can, I guess, right? But you don't have to. Okay, number 3. Number 3 was definitely ratio test, like through and through. You ever see a factorial? You ever see an exponential? You are probably doing ratio test, right? So let's go ahead and do our ratio test. We've got an plus 1 divided by an. And what is this guy going to be? Well, we're going to just do our keep change flip on multiplying fractions. We're going to have 2 to the n plus 1 divided by n plus 1 factorial times n factorial over 2 to the n, right? What does this guy equal? Well, we're going to have 2 to the n plus 1 cancel with 2 to the n, so we've got 2. We're going to have n factorial cancel with n plus 1 factorial, so we're just going to have n plus 1. And this limit here, okay, we've got absolute values here, right? But these are all positive, so you don't need to keep it through. This limit here is obviously 0, which is less than 1. So by ratio test, the sum converges. This is very important. Make sure you're doing this on the test. You're saying, like, if you're on the final or on the makeup or whatever, you've got this test. You want to say, like, oh, I used such and such test. Say by this test, the sum converges. Because if you just write this and you just say converges, of course, when I'm looking at it, right, I'm teaching. I understand that this is a ratio test, but this doesn't, like, you haven't established what is, like, why are we taking this limit? Why does the limit being 0 matter, right? It's got to be less than 1. And so stuff like this, right? Make sure that you're being, like, super precise with your reasoning. Alrighty. That's number 3. Number 4 was kind of, I think that the only way that you're getting this wrong, which a lot of people did get it wrong, but the only way that you should be getting it wrong is just overthinking it, right? Because we look at it here and you're like, okay, alternating series. You have -1, so we've got this sum here. Sorry. We've got this sum here of -1 to the n, 3 to the n over n. So, like, we've got alternating series, right? But notice if you do alternating series, right, this guy here doesn't go to 0, right? 3 to the n over n. Well, 3 to the n grows so much quicker. And you can do a ratio test if you'd like. So ratio test actually would have been valid here. You could have done, some people did do ratio test. But what I would do is just divergence test, right? You're thinking way too hard about it. All you've got to do here is just say an, right? So an equals -1 to the n, 3 to the n over n. This guy does not go to 0, right? This is going to like it's going to be, it's going to be this guy and then this guy and then this guy and then this guy. It's like getting like super, like infinitely big and small, you know what I mean? So since it doesn't go to 0, we just say by divergence test, it diverges, right? And you're probably like, oh, John, well, what is divergence test? I forget that, like, we haven't really been using that a lot. Like, it's so long ago. Divergence test just says that if you're not going to 0, surely your infinite sum is not going to be finite, right? That is, like, super impossible. How am I going to add infinitely many non-decrease, if we're getting small enough, like, okay, we're adding 1 over square, we add 1 over 1 plus 1 over 4 plus 1 over 9, right? This is shrinking enough. It's getting so small that, like, the tail end, you're not going to be adding very much, like, that's meaningful. But if you're adding, like, 3 to the n, at some point you're going to be adding, like, 3 to the 100 is, like, I don't know how many decimal place or how many place values that has, like 50 or something. It's going to be like, in the quadrillions or something. You're never going to add those guys and hope that you're going to get convergence, right? So that's, I would definitely say slow down and take your time, especially on these like series ones. Does the series converge? Think about it for a second. Just think, is there any chance that I believe that -3 to the n on the top is ever going to converge? Probably not. And you just go ahead and do your divergence test there. Okay, let's go ahead and do number 6 real quick, just because it's going to be quicker, and then we can get into the big one, which is our Taylor expansion. So number 6, this one was not too long either. I don't think none of these problems were very long, as long as, like, if you had a good idea, they shouldn't have taken very long. 5 takes a little bit of time. That's why we'll do that last. Construct the series which converges, but not absolutely. Right, we know this. N greater than or equal to 1, -1 to the n over n. Super, super basic. You could do -1 to the n over square root n, or n, cube root n, or whatever you want to do. The whole point is that the easiest one to do, construct the series which converges conditionally, right? Not absolutely, but it does converge. Is this guy here? You just have alternating series. So by alternating series test, and I didn't ask this, so I just asked construct one. If you just wrote this, you get full credit. But I did want, as I wanted this, I don't need the justification. But if you did justify, that's fine, right? So alternating series test, we know that this guy's alternating and 1 over n goes to 0. So check, we're good, right? But it's definitely not absolutely convergent because the sum n greater than or equal to 1 of negative 1 to the n divided by n in absolute value is just the same thing as the harmonic series, right? Which we know does not converge. So then that's going to be conditional convergence. It's not absolute, but it does indeed converge. All right, and we'll get on to our last. We're going to do our little Taylor expansion, and we should be done. Let's go up here. We'll get number 5. Okay. Let's make it happen. Compute the Taylor expansion for f of x equals ln x centered at a equals 2. Okay, so what is always step 1 of Taylor expanding? Well, let's figure out what our derivatives are, right? So you've got f prime of x will be 1 over x. F double prime of x, so we've got x to the negative 1. So maybe I'll even keep x to the negative 1 just so we're super on the same page. X to the negative 1. This guy's going to be negative x to the negative 2. F triple prime is going to be negative, so that's going to be positive. So maybe we'll just say negative 2 x to the negative 3. F to the fourth x, fourth derivative, right, is going to be what? Negative 2, negative 3, x to the negative 4. Okay, so let's look at our patterns. So on the first derivative, we've got a negative 1. Second derivative, we got a negative 2. Third derivative, we got a negative 3. So we know that f, the nth derivative of f, is going to have something x to the negative n, right? Now, what about our coefficients, right? So this guy's 1. This guy, I'm not going to worry about negative signs. We'll do negative signs later. Actually, let's do them now. So we have 0 negatives, we've got a negative, and then we've got a positive, negative, positive. So we're alternating, and whenever you see alternating, you just go ahead, negative 1 to the n, right? Now, is it n or is it n plus 1, right? We have to figure out our offsetting. So let's look at this for a second. We've got f prime is going to be no negatives. So when n is 1, we should have an even power here. But it's not, right? So if this were true, we have negative 1 to the n, well, then we should have negative, positive, negative, positive. But we notice that it's actually positive, negative, which means that we are going to have n plus 1 as our power for negative 1, right? Let's move this guy over a little bit. Okay, and so now we just get down to business with our coefficients. And we notice our coefficient here is 1, 1, 2. 1 times 2 times 3, 1 times 2 times 3 times 4, right? So, but we're having these 1 times 2 times 3 for the fourth, 1 times 2 for the third, 1 for the second, 1 for the first, right? Which means that we figure that this is going to be not n factorial. Sorry, I didn't mean to do that. Not n factorial, but it's probably going to be n minus 1 factorial, right? N minus 1 factorial. So let's go ahead and check this, right? So negative 1 to the n plus 1. That means that our first derivative, well, let's just check our first derivative, right? Make sure they agree. So first derivative, we're going to have negative 1 to the second. So that's positive 1. That's what we want. We're going to have n minus 1 factorial, so 0 factorial. And 0 factorial we know is 1. So that checks out. We've got x to the negative 1. Checks out. So this is good for this one. Let's go to number 2. We see negative 1 to the 2 plus 1 is negative 1 to the third. So that's negative 1. We're good. We've got 2 minus 1 factorial. So 1 factorial again is 1, which we're happy with. And then we've got x to the negative 2. Perfect. And you can just go ahead and check these, all of them. But this is indeed what you would end up getting. So we notice that this does not work for the 0th derivative. So f of x is f like 0, right? This guy should just be ln of x. But instead, we end up getting as a 0 minus 1. We've got a negative 1 factorial. And we've got x to the negative 0. So this does not hold, clearly. But we'll just pull that out of our sum, right? So the sum, so we say that f of x is going to be what? First, we're going to say ln of a, because we're going to pull out our, it's normally, sum n greater than or equal to 0, but we're going to pull out the 0 term, which is ln of a. So we've got ln of a plus the sum now over our derivatives from 1 to infinity, right? And this is just going to be fn of a. So we're going to say negative 1 to the n plus 1 times n minus 1 factorial. 2 to the negative n, right? Because here x, this is fn of x, so we need fn of a. Also, if it helps you, after you do these, just go ahead and write next to them, fn of a is negative 1 to the n plus 1, n minus 1 factorial times a to the negative n, right? And then we divide this guy, remember, by n factorial. And then, so we've got fn of a divided by n factorial applied to x minus a to the n, right? Now, we simplify a little bit. This is going to be ln2 plus the sum, n greater than or equal to 1, of negative 1 to the n plus 1, 2 to the negative n. And what is n factorial canceling with n minus 1 factorial? Well, we'll just have divide by n on the bottom. X minus 2 to the n. All right, perfect. Then we're almost done. All we have to do is check our interval of convergence. So we're going to say, when does this guy converge? Well, we do our ratio test. This ln of 2 is just the number. Ln of 2, like ln of 2, even if it's a 1 quadrillion, which it's not, right? But if imagine it's a super huge number, still, that's not going to affect our convergence, right? Either this guy converges, so then this whole thing is finite, or this guy diverges, so the whole thing diverges, right? So we only need to look inside our sum. We can ignore the ln2 or any like of these finite, additions. Okay, so we're going to go in here. We're going to say ln2. Sorry, I'm tripping. Now let's go ahead and do our interval of convergence. Okay, now we've got our interval of convergence. We want to do our ratio test. So ratio test, we're going to say an plus 1 divided by an in absolute value. Well, absolute value is going to cancel out this guy. So all we care about, is going to be an plus 1 is 2 to the negative n minus 1 divided by n plus 1 times n divided by 2 to the negative n, right? And then we're going to have x minus 2 to the n plus 1 divided by x minus 2 to the n. Forgive me for the order of this not being as good as it could have been. My apologies. Yeah, definitely. You should include this whole thing when you do it over here times this. That's my bad. But you guys get the point. I understand. I think that you guys probably understand this anyway. But if not, convince yourself. Go ahead and do the whole n plus 1 of this divided by the n of that, and you should see the same thing. Okay, so now we cancel, and we're going to get what? Well, 2 to the negative n minus 1 divided by 2 to the negative n. Well, when you divide, you subtract, and so we're going to have 2 to the negative 1. We're going to have n divided by n plus 1. And now we're going to have x minus 2 with just 1 power on it, right? And I guess this should also be absolute values here, right? Okay. And the limit of this guy is what? The limit as n goes to infinity. Well, 2 to the negative 1 times n over n plus 1. Well, we should end up getting 1/2, right? So, or 2 to the negative 1. Okay, I apologize. 2 to the yeah, okay. Let me just rewrite this real quick, just so this makes more sense. So I'm going to drop the 2 to the negative 1 on the bottom. So we've got n divided by 2n plus 1, right? And so now what's the limit of this? Well, we just do, we know from rational functions, this is just going to be 1/2. So we're going to have x minus 2 times 1/2, right? We want this guy to be less than 1, which means that we multiply up x minus 2 less than 1 is what we want. Less than 2, sorry. So x minus 2 is less than 2. This means that we need the distance from x to 2 is less than 2. Well, what numbers are those? You can do your algebra if you'd like. Okay, I multiply negative 2 less than x less than, you know what I mean? But we don't need to do that. We just say that the difference between x and 2 needs to be less than 2. So that's just going to be 0 and 4, of course, right? So x is in 0, 4. And so now our final step is to check our endpoints. Go ahead and check your endpoints. I'm not going to check x equals 0 because ln of endpoints. You could if you'd like, but and it'll be the same, but I just don't care to check x equals 0 because ln isn't even defined there. So ln 0 not defined. So this is clear, right? And then the next one, let's check 4. So f f of 4 is going to be what? Well, let's go ahead and plug it in. We're going to have ln of 2 plus the sum n greater than or equal to 1 of -1 to the n plus 1, 2 to the negative n divided by n times x minus 2 to the n. Well, x minus 2 to the n is really 4 minus 2 to the n, right? And you notice that 2 to the negative n cancels with 2 to the n, right? So now that we've got that, this is going to be ln 2 plus the sum n greater than or equal to 1 of -1 to the n plus 1 divided by n, and we know that this converges by alternating series test, right? This is the exact same one that we were talking about on the extra credit, is that you've got -1 to, -1's alternating, and then you've got divide by n. Then if you really want to be proper, okay, you could say this is -1 to the n divided by n. If you were like, okay, this is, but this is like clear. It's the same thing, right? Okay. So then we know, so then finally, you get x is in 0, 4 with 4 included. And this guy right here would be your answer. All right. That's it for today. I hope that you all have a wonderful weekend. And email me if you have any questions. We'll have the makeup exam on Monday. If you want to take that for practice, email me by, well, so I'm recording this on Thursday. But email me by Friday, like maybe by like 10 or something, because I'm probably going to print them out around noon. So I'm only going to print enough for everybody that's coming. So if you want to do it for practice, I will also be posting it online after people take it on Monday. So if you just want to do the practice, but you don't want to come in at 8:30 on Monday, feel free. But we'll have that, and then we'll have the final exam Monday after. I hope that you all have a wonderful day, and take it easy.